In this class, you're probably going to see the first use of definite integrals for the computation of a quantity which is something other than an area. I'm saying probably because probably some of you have seen this application already in high school, in which case it will be just a review. But as the title says, what we're going to be looking at is how to compute the length of an arc, also called the arc length. Let me introduce the problem that we're trying to solve. We know how to compute the length of a straight segment. Well, yeah, with a ruler, but if actually that segment is on an xy plane, we know that all we have to do is find the coordinates of the initial point, the final point, and use the distance formula. Okay, that's old hat coming from the Pythagorean theorem, and I assume you all know that. But how are we going to deal with the curved arc, with something that looks like that, which may have some straight sections, but overall is just curved? Well, what we're going to do is we're going to follow the same four-step procedure that we use to set up a definite integral in general. Remember, slice, approximate, add up, take the limit. So let's see how we're going to do that in this particular case. So first of all, we're going to slice our arc. So we're going to divide it into small chunks. As before, for convenience, we are going to slice this curve so that the horizontal distance between any 2 points, any 2 consecutive points, is going to be constant, our usual delta x. Okay? Then what we're going to do is we're going to approximate each one of the sections that we have constructed in this way, and we're going to approximate it through a straight segment. So for each one of these sections, the length of the segment that we're using as an approximation is going to be equal to the square root of delta x squared, which is the horizontal distance, so the x2 minus x1 squared that we have in the formula above, plus delta yi squared. Again, as I said, delta x is supposed to be common. It's not really that important, but we're going to do it just for simplicity. While of course the delta y will change. Some of the sections are steeper, some are flatter, so they're going to have different length. Then what we're going to do is we're going to add up all of these segments. So we're going to figure out what is the approximate length of each one of those sections, and we're going to add them all up. And finally, we are going to take the limit as n goes to infinity, thus obtaining an integral. Well, not quite. Look at the formula we have. It looks very much like the definition of an integral, but it is not quite. Can you figure out what's wrong while I move to the next slide? Alright, so if you look at that formula, you realize that there is the differential missing. Okay, where did it go? Well, it didn't go anywhere, it just didn't show up in the construction, but we need it. Remember that differential is not there for show, it is an essential part of the construction. We do need to have a formula that looks like limit as n goes to infinity of the sum from 1 to n of some function times delta x. We don't have delta x. Well, we're going to make it up. How we're going to do that? Well, we're going to take that formula and manipulate it a little bit. What we're going to do is we're going to take the delta yi squared and multiply and divide that by delta x squared. In this case, both terms under the square root will have a delta x squared, which I can therefore take as a common factor, and then move it out of the square root, thus obtaining a delta x. Okay, now I've got my differential, so now I can go ahead and move from the formula that you see in front of you to an integral formula. I may have gone a little bit fast with the algebra here, so if so, rewind, pause as much as you need, and just make sure that you understand how each of the steps is done. Alright, so now what we have is that the arc length formula is given by the limit as n goes to infinity of the sum from 1 to n of the square root of delta x squared plus delta y squared, but I can write that square root in the new formulation which I've obtained, which does include the delta x. So we're going to do that. So now I have an expression that looks very much like a definite integral. So all I have to do now is write it in integral notation. And that's quite easy. All I need to do is I need to write that down as the integral from a to b, whatever a and b are, of the square root of 1 plus, notice delta y over delta x in the limit as n goes to infinity, of course, becomes the derivative of y with respect to x. I'm going to square that and multiply by the dx. Okay, so all I need to do is figure out what the derivative of the function that describes the curve is square it, add it to 1, compute the square root, and then multiply by dx and integrate. Now notice that this formula involves the integral of a square root of a sum of two pieces. So in general, this is not going to be a piece of cake to integrate. In fact, unless that formula nicely simplifies, as it will do in many applications, in fact in most of the testing applications, definitely in all the ones we're going to see at the beginning, or unless we can solve it by using some kind of trig substitution, we're stuck. And so this is a formula, however, it does not have universal computational appeal. But if you think about it, so is true of even the area formula, right? The area formula is going to work as long as we can integrate the function. So maybe we're starting to see the need for doing something in a situation where we cannot integrate in the sense of using the fundamental theorem and computing the antiderivative. Well, that's coming up shortly.